So welcome again to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also do appreciate and see the beauty in the simpler problems. Now, today, we took a small tour away from a look at the exponential slash logarithmic functions. And now we are looking at a very interesting polynomial from the MIT 2022 Integration B regular season question, and that's problem number 14. The problem looks very complicated, but it is actually a very simple problem. So the problem is the summation from n equals to 2 to infinity of the integral from x equals to 0 to infinity of open bracket x minus 1 close bracket times x to the power n over 1 plus x to the power n plus x to the power n plus 1 plus x to the power 2n plus 1. So before I go into the solution phase, I would like to thank our subscribers. Thank you so much for the trust. We are growing, and we really appreciate the support you continue to give us. We don't take that for granted, and that's why we are here. We try to come back here to make it up to you. To our first-time visitors, we would like to encourage you to subscribe to our channel here at Everyday Mathematics. We solve the harder problems. We try and come up with solutions to a problem that may seem a little bit complicated. And this is just for the fun fact that we do enjoy solving the harder problems. For the second, third, fourth, and the fifth-time visitors and beyond, and those who haven't really gotten the motivation to subscribe to our channel, we'll tell you, hey, we'll keep coming back, and hopefully maybe today is the time you get that motivation to subscribe, or tomorrow may be the time, but we're here. And one thing we could probably say is that your support really means a lot to us. Thank you. Now let's go to the solution. So this problem, as you can see, it's intricate, but once we take apart and separate a few things, then it becomes obvious. So this integrand here, if you multiply x to the power n by x and by 1, we get in the numerator x to the power n plus 1 minus x to the power n. And then in denominator, if you factor out x plus 1, as you can see, we are left in bracketed 1 plus x to the power n. Now, what we can see here is that in the denominator, you do have 1 plus x to the power n, and we have 1 plus x to the power n here. So in essence, this is something that is easily factorializable. And so what that means is that in the denominator, we have a hidden 1 here plus x to the power n. So we have that multiplied by 1 plus x to the power n. Now, as you can see, this here is common with this, and then this is common with this. So we can use partial fractions to further simplify this expression. So this expression, the integrand, is the same as 1 over 1 plus x to the power n minus 1 over 1 plus x to the power n plus 1. So this is interesting. This means that we have these sums of integrals, but as you can see, if we begin from n equals to 2, and then we have 1 over 1 plus x squared minus 1 over x plus 1 plus x to the power 3 plus when n is equal to 3 is 1 over 1 plus x to the power 3 minus 1 over 1 plus x to the power 4. And so you see this cancels with this, and this would cancel with the next one. So this is a telescoping summation. Since with integration, this entire integrand and this entire could all be bunched together under one integration sign. So another way of expressing it is that since at the end of it all, we're left with 1 plus x to the power infinity, in reality, we could express it such that this is the same as the limit as k tends to infinity of the integral of 1 over 1 plus x squared minus 1 plus over 1 plus x to the power k. So which can further be simplified by now taking this limit sign over here. So it's the integral of 1 over 1 plus x squared minus the limit of k tending to infinity of the integral of 1 over 1 plus x to the power k. So the first integral, the blue integral, for those of you who know this is as simple as the arctangent with the limits factored in. So we have arctangent of infinity minus arctangent of 0, or and this is actually a very wrong way of doing things. The more correct way is the limit of x tending to infinity of the arctangent of x. Here, the popular thing that we know is that this tends to infinity, not to infinity, but to pi over 2. And then when x tends to 0 of arctangent of x, this tends to 0. So our answer here is pi over 2. Now, for those of you who don't know how we arrive at this, I have a simple derivation here. If we let x to be tangent theta, that means that dx d theta is sec squared theta, or secant squared theta. And so dx is the same as sec squared theta d theta. So this integral here, if we just focus on the indefinite integral, the integral of 1 over 1 plus x squared is equals to 1 over, in place of tangent, in place of x, we have tangent of theta. So this becomes tan squared theta times dx, which is sec squared theta d theta from this change of variables. So in the numerator, this sec squared theta climbs up here, and then now we have 1 plus tan squared theta in the denominator. And for those of us who know these identities, 1 plus tan squared theta is the same as sec squared theta. So this sec squared theta and sec squared theta cancel. So we are left with the integral of d theta, which means that the answer is theta plus the integration constant. Now from here, since we know that x is equals to tangent theta, then what it means is that theta is the same as arctangent of x. So this integral actually here from here is the same as the arctangent of x plus the integration constant. And that's why we straightly put arctangent of x here. So that we know. So the blue integral has the answer pi over 2. What about the green integral? The limit of k tending to infinity of the integral of from 0 to infinity of 1 over x to the power k, we know that for x less than 1, for any value between 0 and 1, the limit of k tending to infinity of 1 over 1 plus x to the power k is equals to 1. And then for x is equals to 1, then limit as k tending to infinity of 1 over x to the power k is equals to 1/2. And then for x when x is greater than 1, the limit of 1 over 1 plus x to the power k is equals to 0. So if we are to represent this on our graph, if y is equals to the limit of k tending to infinity of 1 over 1 plus x to the power k, it means that between 0 and 1, we have everything being equal to 1. Then at 1, we do have half. And then from 1 to infinity, we have 0. So the integration from 0 to infinity is simply the area of that rectangle under this line, which is length 1, height 1. So in other words, the limit of k tending to infinity of the integral from x equals to 0 to infinity, or 1 over 1 plus x to the power k is equals to 1 times 1, which is equals to 1. So the green integral results into 1. We saw the blue integral amounting to pi over 2. So in essence, the summation from n equals to 2 to infinity of the integral of 0 to infinity of x minus 1 times x to the power n over 1 plus x to the power n plus x to the power n plus 1 plus x to the power 2n plus 1 is equals to this blue integral minus this green integral. And that means it's equals to pi over 2 minus 1. And this is the answer of this seemingly intricate problem. But it just did require a lot of patience. A lot of issues come when you assume that this entire thing goes to 0. And I think most people would find that the answer would erroneously assume the answer is pi over 2, but there is this negative 1. So thank you so much for paying attention and also following along. We do appreciate your support. For those of you who haven't subscribed, again, we ask you to subscribe to our channel. We do fun stuff here. Thank you. Until next time, kwaheri.